the August Earth Systems and Climate Change Science webinar series. Today's webinar will be on tropical cyclones in the Australian region, the past, present and future, and will be provided by Tony Rafter from the CSIRO. Tony is a senior experimental scientist in the Extreme Weather and Climate team within CSIRO Climate Science Centre. He's also a PhD candidate at the ARC Centre of Excellence for Climate Extremes. He's part of the current Earth Systems and Climate Change Hub project, Project 5.5 on extreme weather hazards in a changing climate. And he led the development of the Tropical Cyclone Projections Portal, which he'll be talking about in this webinar, for the now completed Hub project, Project 2.8 Extreme Weather Projections. Tony has almost 15 years of experience in developing climate projections of extreme weather phenomena such as extreme rainfall and tropical cyclones, using both global and regional climate modelling techniques. So I think we might dive straight into it. So I'll pass over now to Tony. Thanks.
Terrific. Thank you, Sonia, and welcome everyone to this NESP webinar on tropical cyclones. I'll be talking today about tropical cyclones in the Australian region predominantly, but touching on some other regions of the globe as well, and talking about how tropical cyclones have changed in the past, what they're doing in the current climate, and what we expect them to do in the future. So Sonia just gave an overview of some of the work done in Project 2.8, which includes the Tropical Cyclone Projections Portal, which I'll be doing a live demonstration of later on in this presentation. And we have an ongoing Project 5.5, extreme weather hazards in a changing climate. And both of these projects, 2.8 and 5.5, have focused on several different extreme weather phenomena, tropical cyclones just being one of them. And there's a large group of us working on these phenomena, and I'm looking forward to producing some more interesting work in the next 18 months or so. So to start off, I'll frame the talk to an extent. First of all, I'll introduce some basic concepts around tropical cyclones with a bit of a 101 treatment. Talk briefly about some of the impacts, and then we'll get into observations and trends of the observed climate. And then we can get into what we don't know. Obviously, we don't know what's going to happen in the future climate, but we can examine what work has been done in terms of climate projections. And then we'll dive into a demonstration of a Tropical Cyclone Projections Portal, which, as Sonia mentioned, was produced as part of Project 2.8. And I look forward to showing you that later on in the talk. So, what are tropical cyclones? When do they form and where? So, they're also known as hurricanes, typhoons, and tropical storms, depending on what part of the world you're in. They feature a severe low pressure and cyclonic winds circling in around the storm. Obviously, they develop and intensify over warm tropical ocean waters, not too close to the equator, but then there are other factors that influence where they form and where they don't, and I will come back to that later in this talk. When they are forming, as they get more organised, they develop more symmetry around the central core of the storm, and when they've developed, they often develop a very well-defined eye. We've got a couple of satellite images on the right-hand side of the presentation there. The top one being Tropical Cyclone Ingrid, which struck Queensland and across the top end back in 2005, and that's got a really nice eye. And you can see the rain bands spiralling in a clockwise fashion. The image below that is from the Northern Hemisphere, and that's of Hurricane Ivan, and we can see the rain bands circling in the opposite direction, going anti-clockwise. They also featured very strong winds. It's probably what they're best known for. But the naming conventions and severity definitions, like the various tropical cyclone categories, vary across regions, and that can be very confusing. So what we call a Category 1 tropical cyclone would be a tropical storm in the North Atlantic, and in various different basins. They've changed the definitions depending on whether you're looking at 1 minute average, 3-minute average, or 10-minute average wind speeds. So it can get a bit messy when we're trying to look at data across the globe, but there are ways that we can deal with that, which I'll come back to. Tropical cyclones and hurricanes also produce storm surge and large sea swells, which can have dramatic consequences, and of course produce a lot of heavy rainfall as well. So this is a breakdown of the structure of a tropical cyclone. There are essentially two main circulations. The primary circulation is where the winds are circling around into the centre of the storm, and that's where we get the horizontal wind speeds that we're talking about, of anywhere from around 70 kilometres an hour when we get a Category 1 tropical cyclone, all the way up above 200 kilometres an hour, pardon me. And that's the winds cycling around tangentially to the storm, so represented by this arrow going in here. So that's where the winds are spiralling around near the surface. And then there's a secondary circulation, which involves air being brought in from a large radius around the storm, and eventually the air traverses in towards the centre of the storm and gets lifted up through these big convective cells, cool, and then moved back out away from the centre of the storm. The figure at the left here is a diagram of what a mature tropical cyclone or hurricane in this case looks like, where we've got rain bands circling around the centre of the storm and intensifying as they get close to the centre. And this is also nicely displayed in the image on the right, which shows a transect through the centre of a typhoon in the northwest Pacific. And there we can see the rainfall in the typhoon, the bands going all the way around the storm and intensifying as we get closer to the centre of the storm. And they get particularly vigorous near the eye wall, where they lift up above the level of the other convective storms, and you can see the cirrus anvil flowing back out over the top of the storm in the outflow. So this is what it looks like being inside the eye of a tropical cyclone, or in this case, Hurricane Katrina, shortly before landfall. And these are images from a set of airplanes that NOAA call the hurricane hunters, that actually fly through hurricanes in the North Atlantic, taking observations. And you can see, if I tick through these images, that it's essentially a big open bowl. It's a very amphitheatre-like effect, and you can even see some of the cirrus being blown out the top of this severe convection. That's looking back the other direction. You can really see it's almost like looking at a grandstand of the MCG or SCG or something like that. It's a very impressive sight. So when do tropical cyclones form? They can form from almost every month of the year except for the depth of winter. So it's ironic that we're talking about tropical cyclones now. There are 0 tropical cyclones on record in August, thankfully. In the Southern Hemisphere, you'll notice here the Northern Hemisphere is organised from January through to December, and the Southern Hemisphere is organised from July through to January, to highlight that they have virtually the same annual cycles. But the overall global climatology of cyclone counts are dominated by the Northern Hemispheric signal, because they have far more typhoons and hurricanes in the Northern Hemisphere than we do in the Southern Hemisphere. So breaking down to the Australian region and the basins either side of us, we have a relatively consistent maximum season from from January through to March, and then it drops away from there, about half as many in December and April as the peak months. So we get about 2/3 of our tropical cyclones during that January to March peak. And here we're talking about where tropical cyclones form. So it might seem straightforward. After all, in my introduction, I said that they form over warm waters near the equator. And that was what various scientists discovered in the 1940s and 1960s, that tropical cyclones or hurricanes really needed warm sea surface temperatures in order to form. And a couple of thresholds were determined, typically 26 or 27 degrees initially, and then that was refined to 26.5. And that works reasonably well in the summer months, but it gives far too many false positives in the winter months. So a group of researchers within our NESP 2.8 project developed a new diagnostic to help better determine where the actual tropical cyclone formation boundaries lie. So in this image here, we've got the dashed line representing the 26.5 degree isotherm, and the dashed dot line representing 5 degrees from the equator, where there just isn't typically enough vorticity or like a spinniness for tropical cyclones to develop. Each of the red dots here are storms that developed into the equivalent of a tropical cyclone, and the blue ones are storms that began to spin up but then didn't develop into tropical cyclones. So I guess we're mostly focused on the red dots in this image. And we can see that whilst the dashed line and the blue shaded area does cover most of the cyclones that do form, there are some regions where it doesn't perform so well, like the southeast Atlantic, close to the equator, just off Africa, and even parts of the Pacific it doesn't do so well. And then there are large regions where we do have adequate sea surface temperatures, but we don't get tropical cyclones. So in order to address this, Kevin Torrey and co looked at some other atmospheric conditions that are required or are deleterious for the formation of tropical cyclones. So they incorporated things like relative humidity and potential intensity, which is largely derived from sea surface temperatures, but also looked at the vertical wind shear. And vertical wind shear is simply a measure of how differently the wind is travelling in terms of direction and speed at different levels through the atmosphere. So if the winds at low levels are travelling much more slowly than the winds at high levels, that induces a lot of shear, and it doesn't allow the cyclone to develop a nice symmetric cyclonic structure. So as a result of these improved boundaries, we get much improved capture, I guess, of where tropical cyclones form, particularly in the equatorial Atlantic and the central equatorial Pacific in both the north and southern hemispheres. And it really has collapsed the regions in which tropical cyclones form in the Australian region as well. We don't get, it extends even further into the southern Pacific Ocean. So this improved understanding of where tropical cyclones form has actually also helped us understand why some global climate models have unrealistic geographic distributions of tropical cyclones. And we can now peg back some of those changes to perhaps a model has too high or too low relative humidity, or excessive wind shear in a particular basin that influences the projected change in tropical cyclones. So on to some impacts of tropical cyclones. So why do we why do we care about tropical cyclones? Well, they're among the costliest natural disasters to regularly impact Australia, and frequently we hear figures about insured losses and overall losses and hits to GDP and things like this in the hundreds of millions or even billions of dollars. And these impacts are caused by the very strong winds and rainfall, and these cyclonic features can cause infrastructure damage, damage to the environment, damage to various sectors of the economy, such as agriculture, and of course imperils life. And it's not just wind that we have to worry about, but flooding is also a major component in these adverse impacts. An example, fairly recent history in the United States, Hurricane Harvey made landfall just near Houston in the Gulf of Mexico and basically stalled over that part of Texas and produced a phenomenal amount of rainfall, which overwhelmed the city of Houston and flooded from all of the bayous and through a very large area of Houston, both commercial, industrial, and residential. So it can have disastrous impacts such as that. It is also important to note that sometimes the rainfall from tropical cyclones can be very beneficial. For example, when they track inland in Australia over regions that have very low rainfall climatology, it can really bring life to a region. So it does have benefits, including topping up reservoirs and so on, when particularly for regions that have been suffering from drought. But in terms of the mortality caused by tropical cyclones, and bearing in mind this is a US context, it's rainfall and freshwater flooding that does create quite a big problem in terms of mortality related to tropical cyclones and hurricanes. So this study from back in 2000 showed the proportion of hurricane-related deaths for the 30-year period from 1970 to 1999, and they found that the majority of deaths associated with hurricanes in the US were related to freshwater flooding, which is interesting because most people think of wind as being the most damaging component, but the freshwater flooding is obviously a big factor. But then they came back to this study and updated their statistics more recently. And now, with the benefit of extra data up to 2012, which of course incorporated Hurricane Katrina, we can see what a disastrous storm surge combined with flooding can do. So they've combined most of the deaths from Hurricane Katrina are bound up in that storm surge figure, which arguably is partly from riverine or rainfall related flooding as well, given that the levees from Lake Pontchartrain failed. But nonetheless, most of the mortality in certainly in American hurricanes is related to the rainfall and the storm surge factors. The paper that developed that statistic on the top right also came up with this, I think, quite salient point, that the deadliest storms in their database weren't necessarily the strongest at landfall. So only 3 of the 10 that caused the most mortality were rated as a category 3 or higher, which is roughly equivalent to our category 4 when they came ashore, and 6 were only equivalent to our category 1 or 2. So that really shows that we need to plan and prepare very carefully for every storm and not just worry about the big ones. And the impacts of tropical cyclones aren't necessarily just related to the locations at which they make landfall. This is a fairly shabby example, perhaps, of an economic impact of tropical cyclones, but certainly it made a lot of impact in the media at that time when Tropical Cyclone Larry and Tropical Cyclone Yazi later in 2011 made landfall in northern Queensland and basically decimated the banana crop, which led to a surge in prices and knock-on impact for Australia's broader economy, with the Reserve Bank claiming that, I think it was the Reserve Bank, claimed that it induced an increase in the CPI index by half to 1%, I think. So, yeah, it's important to note that it's not just directly impacted people or communities or businesses that are affected, but it does have flow-on effects through the rest of our economy. So on to some observations and trends of tropical cyclones, and a lot of what I'll present in this part of the presentation comes from a fairly recently published report, a review published in Wire's Climate Change, which is a review of tropical cyclones in the Australian region, with an author list composed almost completely of people who have contributed to the NESP 2.8 project. So this plot shows annual tropical cyclone frequency in the Australian region, dating back to the late in the first decade of the 20th century. And at first blush, it looks like there's some really major trends. We go from having about 5 a year for the first half of, well, most of the first half of the 20th century, and then all of a sudden we've got 15 in the 60s, 70s, 80s, and then it settles back down again. But really this just reflects that our observational capabilities and the way that we detect and determine what is and what isn't a tropical cyclone has changed over time, and this this makes doing any trend analysis particularly tricky when dealing with tropical cyclones. And that doesn't just apply to the Australian region, that's a global problem. Basically, before we had remote sensing capabilities such as radar and satellites, we were reliant on tropical cyclones or hurricanes actually coming ashore, or shipping coming across them and being certain enough that it was a tropical cyclone of a certain intensity, I guess, based on wind speed or wave height, things like that. So improved satellite imagery and refinements to how we diagnose tropical cyclones from that imagery has really improved our ability to predict with confidence where tropical cyclones are and where they perhaps aren't quite tropical cyclones yet. And so we tend to use data from about 1980 or 81 onwards for trends and looking at intensity changes. Pardon me. The Australian average, the Australian region now averages around 10 to 11 tropical cyclones per year. So this is what our tropical cyclone climatology looks like around Australia. These are tropical cyclone tracks that pass anywhere within the Australian region, anywhere between the 90-degree east and 160-degree east longitudes, and between 5 degrees and 40 degrees south of the equator. The tracks here shown are from 1981-82 through to 2017-18. And they are coloured by what category they were at that point of their life cycle, with white being the lowest severity, going through light blue, blue, and then through the yellows, oranges, and red for a category 5, which thankfully aren't that frequent in our part of the world. And this is what the same track climatology looks like when converted into a density. So this is the average number of tropical cyclones per decade, and that's been organised onto a 1 degree by 1 degree grid for it's a slightly different period, but much the same. And we can see that most activity in tropical cyclone appear off the northwest coast and along the northwest coast of Australia, up to the top end, a region of enhanced activity in the Gulf of Carpentaria, and then a region just off the Queensland coast. Coming back to the tracks, we tend to break down the regions that we discuss statistics and so on of tropical cyclones in the Australian region into various basins. And in the review paper that I mentioned earlier, they've broken down these regions into three sub-basins. So a western basin that goes from the 90 degree to 125 degree longitudes, a central basin there, and an eastern basin as well. But then we can also, and we have also split the Australian region domain into an East Australia and West Australia domain in a tropical cyclone portal, and in some of the statistics in plots to come. And where we have a central basin in the portal, we've used a slightly different domain, but much of the statistics remain consistent between those. So this plot just shows how we can look at some of the behaviour of tropical cyclones in the Australian region broken down into these various subdomains. The numbers here show the tropical cyclones that form in each of these regions, and then in brackets is the number of tropical cyclones making landfall over Australia at some point of their lifespan. So when we look at the red numbers there, the landfall is roughly equally split between east and west, but the proportion is much higher in the east. That's largely due to the fact that we've got much more ocean to play with out to the west, and so there are more tropical cyclones that travel out in the Indian Ocean and they don't make landfall. Whereas when we look in the black numbers there, which are the subdomains in the earlier slide, the central region is a region I'll point out is quite interesting because almost 3/4 of tropical cyclones in this central region make landfall at some stage. So that's a region that we have to take, I guess, a bit of extra notice of when we are forecasting tropical cyclones. So this slide shows some work done by Sally Lavender and Andrew Dowdy, breaking down what the tropical cyclone climatology is in the Australian region. Shows things such as the number of tropical cyclones, and this is on a 5 degree by 5 degree grid. The number of cyclones that fall within each of those bins, and also their direction and the proportion of storms that are travelling at what speed. And the numbers in red show areas where they are on average intensifying, and the blue is where they are decaying on average. And the large black outlined arrow shows the average direction of the tropical cyclone, and we can see that particularly for the western domain, about west of 135 degrees east, the tropical cyclones have a distinct recurvature on average. So in the kind of top row, the 10 degree south row, they tend to move down towards the west, and as they traverse further away from the equator, they start to recurve and move and get captured in the westerlies and recurve around to the west. It's a little less clear in the tropical Pacific Ocean near Australia of average direction. It tends to, well, they don't seem to have a tendency to move one direction or another. much more variable in their path. So on to some trends in the Australian region. We've already seen through this review paper they've published recently that there are significant decreasing trends in the number of tropical cyclones in the Australian region. So these trends are significant for all tropical cyclones and also for severe tropical cyclones, which we typically is category 3 and above. So that's for the overall seasonal frequency. They also looked at trends in the frequency of landfalling tropical cyclones. And interestingly, for all tropical cyclones, the trend is not significant. And that's probably due to those 2 years in the late 1980s and 1990 where we had virtually 0 landfalling tropical cyclones in those years. Yet that wasn't enough to make the decreasing trend in the severe tropical cyclones non-significant. So that is a significant decreasing trend in landfalling tropical cyclones, which does agree somewhat with some of the projections that I will talk about later in this talk. So these recent decreases, or downward trend is due to recent decreases in the western and eastern basins and decreases during the peak season through January through March. I'll mention briefly that there has been some work done internationally and within Australia on ways in which tropical cyclones might be moving away from the equator. So there is this plot shows some work by Cosson et al. From 2014, American-based scientist, who looked at trends in both hemispheres of the maximum lifetime intensity, the latitude at which the storm reached its maximum intensity. And the red curve here is from the best track historical data set, which we use extensively and is used in the portal. And the blue curve is from a satellite-based data set. And both of those have significant poleward trends. So the distance from the equator is up this end, and over time it appears that tropical cyclones are reaching their peak intensity further from the equator than they did before. And genesis also appears to be occurring further from the equator. These images, these plots are from a paper by Shamila and Kevin Walsh, who are also members of NESP Project 2.8, and they broke down the genesis locations of tropical cyclones in 2 periods, one from 1980 to 1997 and one from 1999 to 2014, and found that genesis in blue in the earlier period were occurring closer to the equator than they are in the later period. So that does give us some indication that perhaps tropical cyclones are tending to form further from the equator on average. The South Pacific and South Indian domains, which are the bottom row of these images here, are significant differences at the 10% level. So they are getting towards what we would consider a strongly significant result. So getting on to some climate projections information now. I'll start off with what appeared in the 5th assessment report of the IPCC, where the general consensus in the literature is that we expect a reduction in total tropical cyclone numbers, but with more reaching high intensity. In this particular image, the blue boxes show the changes in projected tropical cyclone frequency, which are expected to go down globally. for the Southern Hemisphere and also for the two basins closest to Australia, the South Indian and the South Pacific. The El Nino Southern Oscillation is very important for tropical cyclone frequency in the Pacific and therefore for the Australian region as well. Some work that Savin Chand, who was lead author of the review paper and part of the NESP team, used one detection method to look at tropical cyclone changes in CMIP5 models and saw that reductions in the South Indian Ocean off Western Australia occurred for both El Nino and La Nina phases. So in here we've got a strong reduction in both El Nino and La Nina as well as overall. But reductions for Queensland on the eastern seaboard of Australia were reduced for El Nino, but not for La Nina. So it was an interesting result. And we have probably will look at this again during the Tropical Cyclone Portal demo. So drilling down a bit more to regional and national scale kind of results, when we do a domain average, we get these kind of numbers out where, so this is work done recently for NESP as well in Project 2.8, looking at two different detection methods now. One is CDD, which stands for the CSIRO Direct Detection Technique, and OWZ, which Savin Chand used in the previous the paper in the previous slide, stands for Akubo Vice Zeta parameter detection. They use slightly different methods to determine the presence or otherwise of tropical cyclones and track them, but they produce quite consistent results. So the bar plots here show actually the interquartile range, so the middle 50% of the model's projected frequency changes. And we can see that the changes in the western domain are larger than the eastern domain, which actually cross zero. So that is in broad agreement with what Savin found in his earlier paper. Another way of looking at projections was done by Samuel Bell, who's also a member of the NESP 2.8 team, where he clustered tropical cyclones into formation regions, which are shown in the different colours in the top panel there. And these projections, so they use these clusters to form projections from various ensembles of models using the OWZ technique. And they found that there were fewer tropical cyclones in future for the Australian region in general, but there were far fewer in the western domain, from about 130 and west of there. So what we're seeing is a fairly consistent signal, a consistent finding for different model methods shown here and elsewhere of large decreases in the South Indian Ocean, and we'll look at that in the TC portal as well. Excuse me. So what about intensity changes? The focus here is on the red box, this lifetime maximum intensity. So projected change in tropical cyclone intensity is still one of the great unknowns, really, because most of our modelling is done with global climate models, and they're not really fit for purpose for analysing intensity because of the resolution at which they have to operate. Nonetheless, for the from the fifth assessment report, once again, we can see slight increases in percentage terms of global lifetime maximum intensity projected. And similarly, the Southern Hemisphere has much the same result. Because of the poor resolution of our global climate models, some modelling centres are using higher resolution simulations to get a better handle on intensity changes, but don't have time to show all of that here. I will show one aspect of one of the downscaling experiments, which does show some evidence of increases in rainfall rates within the central part of the most intense storms. So this is looking at the rainiest 10% of tropical cyclones in some downscaling experiments run by a group in the US, which show enhancement to rainfall within the inner roughly 200 kilometres or so of the storm. Right, so now I'm going to start doing a live demo of the Tropical Cyclone Projections Portal. It was developed to help researchers and stakeholders investigate projected changes particularly in the spatial distribution of cyclones in the Australian region. So at this point, I will try to change the screen that I'm sharing. Here we are. Okay, so this is the welcome screen to the Tropical Cyclone Projections Portal. I'll just firstly explain the layout. We've got an introductory tab, which has a lot of documentation of the various features and methods and data and so on, which I'll scroll down, excuse me, in just a moment. And then we've got each of the features of the portal in tabs across the top of the screen here. Pardon me. Getting over a cold. So in this introductory page, I'll start with a disclaimer that the portal is basically designed to provide exploratory analysis. And if you do want to get into larger decisions about what to do about changes in frequency of tropical cyclones, I suggest you get in touch with NESP and we work through with qualified climate scientists how to interpret and use the data. But moving on to the intro tab in this documentation, I'll just scroll down the page here. We go through each of the features, and there are a number of links to each of the sections of the documentation. And the various features, the methods that we use to determine or to discover tropical cyclones in the climate models, talk about how we developed and determined the phases of ENSO in the models. We talk about the various ensembles or combinations of global climate models, and how we have combined them, the various data sources, the observational and model data, and recently we've added a glossary in addition to references, acknowledgements to developers, and the opportunity to contact us with any feedback you have regarding the portal. So scrolling back up to the top, we'll start with looking at the observed tracks. So these are tracks from IB tracks, which is the global best track data set. And this is defaults to 1981 to 2010, which is our default observational benchmark. Here we've just got all of the tracks in blue, but we can also filter them and colour them, pardon me, by phase of ENSO. And we can select various subdomains. So this is all of the southern hemisphere, but we can choose storms that pass, once again, just between 90 degrees and 160 degrees at some point of their life cycle, and various other subdomains. So the West Australia, Central Australia, and East Australian domains. And we can also choose in this panel up here to select or deselect the track or the genesis location. So if I unselect the track, we can just see the first detected point of where they were declared a tropical cyclone. And we can also do this for various global climate models. So once again, the tracks default to this blue colour, but we can also filter by the various phases of ENSO. And we can look at the CSIRO direct detection method or the OWZ method, and they give slightly differing results. And we can also look at various subdomains as before, and different climate models. Now, that's very pretty, but it doesn't tell us a whole lot about how things might change. Even if we go from a baseline period to a future period, it doesn't really, it doesn't really tell us a whole lot. So we need to go towards a density in order to determine differences between baseline period and a future period. But we have a slight problem. In order to combine the models, we need them to be roughly equivalent to each other. Otherwise, when we do a straight average of different models, models that have too many will pollute the climatology, and models that don't have enough will pollute the change signal, will dominate the change signal. So this tab, the annual frequency tab, shows the distribution of the number of tropical cyclones per year in each of our climate models listed across the bottom here, and comparing that with IB tracks, which is the observational best track data set. And these are the models that we have examined using this CDD technique. We have a similar variability around tracks developed, detected using OWZ. So what we have needed to do is basically rescale from the historical climate period to roughly be equivalent to the average tropical cyclone frequency in the Australian region. And by finding that normalisation or scaling factor, we've been able to produce, to multiply that factor by the density of tropical cyclones to produce ensemble average changes of tropical cyclone density. Pardon me. I'm losing my voice. And so we can get an ensemble average, and we've done ensemble averages for models that are common to both of the CDD and OWZ detection, ones that we use both techniques for, and also an ensemble of best available. So this plot here is showing the baseline period of 1970 to 2000. We can also look at the future climate period, but where the rubber really hits the road is where we get to the differences from the future to the baseline. And this is where we can see some of the spatial patterns of change in tropical cyclone frequency in the density fields. And for example, so this is using the CSIRO direct detection technique for the full year for our best available models. And we can see that there is a bigger decrease in the Indian Ocean, and particularly off northwest WA, than there is off Queensland. And we can also interrogate the various phases of ENSO to see what difference the phase of ENSO makes. So this is the La Nina phase of ENSO, and we get a fairly similar signal. In the neutral phase, we have quite a strong decrease in the South Indian Ocean under neutral ENSO conditions. And under El Nino, we get an interesting signal, particularly off the east of Australia and the South Pacific Ocean, where we get some increases and some decreases, and along the Queensland coast, very close to zero. The OWZ technique, which was used by Savin Chand, is also in here, and we can look at the equivalent plots and find fairly similar outcomes for El Nino and La Nina, although we've used potentially a different definition of different time periods and so on. And we're using, I should have mentioned, we're using RCP 8.5 for all of our future climate simulations here. So we're getting pretty much the strongest signal that we can. So moving on to the next features quite quickly now. This is quite an interesting feature, but it's still under some development. This is a coastal crossings feature. At the moment, it's presenting here the density of tropical cyclone tracks crossing each 100 kilometres of each of these line segments. So they're normalised by their length. And we can see that the hotspots of activity for coastal crossings are off northwest WA here and through the Gulf of Carpentaria, much the same as our density, our observed density plots showed earlier. But we also have the ability to look at individual climate models currently. And in this particular model, we have a region across the northwest of increased track activity in the baseline climate. We can also look at differences between future and baseline and differences between the observations and the model. And those are all there to play with, although we still need to implement our ensemble combination, which will give more coherent answers and a smoother signal. Individual models give quite different responses, so we're keen to get the ensemble changes, pardon me, in there fairly promptly. One thing I'm quite excited about in terms of being able to combine models together is to determine, on average, what time of year we might see the most changes. So in this panel, we can look at the seasonal cycle of tropical cyclones and compare it with observations, which is this black dotted line, and compare it with the average of the historical and the future RCP 8.5 tropical cyclone counts from our ensemble of models. So we've got various ensembles, the common with the OWZ technique and the ensemble of 11 best available. And we can see that the historical climatology is a little bit too high in some months and a bit too low in others. It does a reasonable job. And we are getting decreases pretty much across the year in terms of proportion. We can also divide this into the various phases of ENSO, and this shows that we are under-predicting tropical cyclones in the Australian region under La Nina, whereas we're over-predicting slightly under neutral conditions and also El Nino conditions. But nonetheless, we can split up the phases of ENSO and look at how tropical cyclone frequency is expected to change in various subdomains. And one last panel, here we're looking at the relationship between changes in frequency of tropical cyclones with larger scale atmospheric fields. So this plot has a bit going on, but it was inspired by the Climate Futures framework, which was used in the Climate Change in Australia website, which divided models into various bins of warm, much warmer, hotter, much hotter, and so on, and various changes in mean rainfall. So along the bottom here, we have change in mean surface temperature across northern Australia from 2 degrees all the way up to 5 degrees here, and change in mean rainfall from a reduction of, I think it's 40% roughly, Mark 3.6, and to plus 25% here. And we see that we have a almost linear relationship between models with much wetter being not as hot, and models that are much drier being much hotter. And we also have a relationship between the magnitude of change in projected numbers of tropical cyclones. Where the hotter and drier the model is, it does appear that they also have bigger decreases. The odd ones out here are IPSL2 models, which had some strange things going on in the annual frequency. So we did actually exclude them. They are these ones down here. So with that, I'll duck back to my presentation just to finish off. I'll get it up. There we go. Okay. So to conclude, just some final comments on observations in the Australian region. So through the NESP 2.8 project, our understanding of the tropical cyclone climatology in the Australian region has improved, and we've found evidence in observations for a poleward movement of the location and genesis of tropical cyclones. And there's also evidence in the literature for a poleward movement of the maximum storm intensity of tropical cyclones in the southern hemisphere. And there's also a downward trend in frequency overall in the Australian region in both all storms and the most severe. In terms of projected changes, we expect tropical cyclone frequency to, decrease by the late 21st century, with some regional differences and changes under different phases of ENSO. And there is some evidence in the literature for increased intensity in the future. So that's all I have for you today. Hopefully that's been informative, and look forward to taking some questions if we have time. Thanks, Sonia.
Thanks, Tony. Thanks for a wonderfully informative presentation, and also for showing us the Tropical Cyclone Portal. We have just a couple of minutes. I think we can squeeze in some questions. So do put your questions in the chat box while we talk. We've got a question from Nick, who asks you, Tony, why is there a time gap between the observed and the future 2070? Does data exist for 2040, 2050?
It does, but not in the Tropical Cyclone Portal. So the project we were working on, we wanted to use multiple methods for detecting tropical cyclones in the GCMs. And one of those methods only utilised 2 30-year windows, so that was what we were basically stuck with, because we wanted to be able to compare these methods directly. But the tropical cyclone tracking does exist, certainly for the CDD method, all the way from, I think, 1960 to 2100. So the data is available, and we can look at changes in other climate periods. Yes.
Fabulous, thank you. And then from Andrew, we've also got a question who asks, Tony, any plans to include other modes of climate variability to the NESP TC Projections Portal?
Other modes of variability, I imagine they mean things like the IPO or the IODs, the Indian Ocean Dipole. We don't have plans at the moment to really extend the Tropical Cyclone Projections Portal to do other large-scale features. So it probably will stay much the same as it is, I'm afraid. It would be interesting to look at relationships between, particularly for Western Australia, relationships between the IOD and West Australian tropical cyclone frequency, but I don't think we have scope to do that in the portal at this stage.
Okay, we've just got 2 more questions, and I think we'll just squeeze them in for those interested. David asks, given the impacts from rainfall and storm surge, could you comment on the net increase in risk from tropical cyclone storm surge and rainfall, given reductions in frequency but increases in storm surge or increases in rainfall?
Right, that's a very tricky question, and it's one that I don't think I can probably give an adequate answer to. Obviously, there is a trade-off between the potential for increased intensity of tropical cyclones and a reduction in frequency. But in terms of how that relates to storm surge, I think that's probably a deeper research question than what I could come up with an adequate answer for here, I'm afraid.
No worries. All right. Gavin asks, wondering if anyone is or has developed a monthly tropical cyclone rainfall versus other rainfall data sets or projections. He's interested in simulating the impacts of tropical cyclones on vegetation dynamics.
Right. Look, I'm not sure that they have. I know there are people working on the relationship between tropical cyclones and rainfall, and particularly extreme rainfall. Perhaps the way forward on that might be to discuss with the Bureau what data they have available in terms of rainfall associated with tropical cyclones, but I don't know that we have investigated that at this stage. No.
Okay, no worries. And Gavin, if you're interested in that, you can email us and we can put you in touch with the appropriate person at the Bureau. So just a very last question, we'll squish it in, from Clarissa. She thanks you very much for the presentation, Tony. And then she asks, in terms of the fundamental conditions for tropical cyclone formation, do we understand what is changing into the future that would cause a reduction in tropical cyclone formation?
It depends on the model, because there are quite a lot of models to look at, and they all have quite a different internal climate. The changes differ from model to model. So some models have changes in the relative humidity field, for example, that mean that the atmosphere isn't moist enough for tropical cyclones to develop. And in other regions of models, the magnitude of wind shear might change. And so if the wind shear goes up, that makes it harder for tropical cyclones to develop properly, as I mentioned before. So look, it's different between models and it's different between regions within models. So it's a difficult question to really pull apart and answer adequately here. But there is some understanding of what's driving changes in certain models, and people within this project have actually looked at that in some detail, but not myself.
Alrighty, thanks, Tony. Well, I think we might wrap up because we're 5 minutes over time. So just want to thank you, Tony, for a fantastic presentation, and thank all our attendees for coming along. Just a reminder that we do record all our webinars, and a recording of this webinar will be up on the Earth Systems and Climate Change Hub website by the end of the week. And also just a quick plug for next month's webinar, which will be provided by Michelle Ho from the CSIRO on assessing future climate risks and adaptation options for Australian water systems. And that will be held on the 17th of September from 2:30 to 3:30 again. So you'll receive an email as usual about that upcoming webinar. So finally, if you have any questions or inquiries about today's webinar or future webinars, up on the screen now is how to get in touch with the Hub. So we thank you once again for attending and look forward to seeing you at the next webinar. Thank you.